Hello my dear students, good morning to all of you. Today we are going to discuss mechanism of micelle. Okay, what is the example of micelle? In the last class I have taught that. If suppose, let us take, soap solution. Soap is nothing but sodium or potassium salts of fatty acids. Am I right or not? Salts of fatty acids. Okay. So, in generally, we may write the formula of this soap is RCOO minus Na plus or RCOO minus K plus. Okay. It is a sodium or potassium salts of fatty acids. Here alkyl group, R is a alkyl group. R is alkyl group. Okay, generally here this alkyl group is a long chain. Okay, this is a long chain group. Is it right or not? So this long chain means this alkyl group consists of large number of carbon atoms. If suppose we'll take more than C17 also. C17 H35 COO minus Na plus. This is a sodium stearate. Generally we are using in the soup. Sodium stearate. This is the commonly using the soap solution. This is a commonly using the soap. This is the formula of common soap. So in this case what happening, sir? Generally these alkyl group. So when we are going to dissolving in water, when I am going to dissolving in water, this soap solution dissociate into RCOO minus alkyl group as well as Na plus ions. Now this group, this is the bulky group of alkyl group. Then I am going to representation in this this is the alkyl group and this is the COO minus. This group means this whatever it may be part has two parts. One is the non-polar part. One is a non-polar part. It is called as tail or hydrophobic end. Next, this is called as CO minus. This is called as a polar head or ionic head. Polar head. By I am writing hydrophilic end. Are you getting my point? So now what happening in the mechanism, soap mechanism, when it is formed in a solution, when I am going to treating with water, this two ends are forming. These two ends, one is the alkyl group containing end, this is called as a non-polar part. One is the CO minus group containing part, this is called as a polar head and hydrophilic end. So means this end is not reacted with water because hydrophobic. This end is reacting with water, hydrophilic end. Are you getting my point? So what happening, for example, if suppose I am going to taking water solution. In this I am added the soap. Then what happening, the minus end will be comes here like this. Then after that what happening, this whatever it may be ions, gets pulled bulk of the solution. Gets pulled into the bulk of solution. In this case what happening, simply these whatever it may be non-polar groups, comes into the center and hydrophilic ends come into the outside, means these are contact with water and it forms spherical micelle. This pair is consist of in towards the center it is having the alkyl groups and it gives the outwards total ions. Okay, ionic group for there. So now micelle is formed. When it is forming, sir, at CMC. Okay, micelle concentration. Yes, am I right or not? Okay, critical micelle concentration. Okay, this is forming like a sphere. Okay, this is the mechanism. Now what happening in the cleaning action? When I am going to talk about the cleaning action, okay, in a cleaning action, what happening here? See, if suppose cleaning action of soap. In this case, what happened? Simple thing is here. If suppose normal dust particles are there, normal dust particles were there. So in that case, what happened? While keeping in the water, the dust particles can remove. If suppose, okay, any oil pot, okay, oil droplet, okay, contain in our cloth. Okay, so in such case, what happening? First of all, okay, hydrophobic ends can contact with, or okay, they are going to directly, what happening here? Simple thing is there. CO minus group is, okay, loving to the water. So that's why these are the outwards. Okay, generally these are outwards, minus charges, all. But alkyl groups are generally react with, or it can surrounded by, these alkyl groups are surrounded by, okay, grease or oil. Okay, then after what happening? The sphere is forming. This sphere is forming, okay, surrounding of this oil droplets, and this hydrophilic ends can contact with water, and they pulled out the whatever it may be oil or grease present on the cloth. See here, in this case, what happening? See, now all are these like this. Okay, this is the what's our oil droplet. This is the oil droplet. Now these are all hydrophilic ends. Okay, these are the hydrophilic ends. Sphere is formed. Okay, this sphere is pulled out. Okay, this oil is pulled out from the, okay, whatever it may be, cloth. This is the action of cleaning action of, okay, soap. Okay, in this way the soap is cleaning the whatever it may be oil or grease particles in our cloth. It can remove in this manner. So if suppose, for example, what about the detergents are? Okay, soap and detergent little bit different is there. When I am going to talk about the detergent is nothing but, okay, RSO3, okay, I am writing RSO3 minus Na plus by RSO3, okay, minus Ca plus. Okay, in the case of, I am going to talk about the detergent. Means detergent and whatever it may be, soap has same formula, but difference is what there. Here organic acid is there, here inorganic acid is there. It is there. Detergent is a sodium or calcium salt of sulfonic acids. But here, okay, what is this, sir? Fatty acids. That only difference. So remaining mechanism is same. As usual. Means detergent and soap is, okay, cleaning the whatever it may be clothes, okay, in the micelle mechanism or micelle mechanism. Are you getting my point? So now we'll go to the next point. Preparation of colloidal solutions. Preparation of colloidal solutions or colloids. In this case, actually, we are using different methods to prepare the colloidal solution. In this first method, aggregation method. First method is aggregation method. Okay, this method is also called as chemical method or chemical preparation. This method is called chemical method or chemical preparation method. In this case, what we are doing, simply while using the chemical reactions, Okay, in this case, what we are doing while using the chemical reactions, using chemical reactions, okay, dispersion, okay, can be done, okay, or colloidal dispersion can be done. Colloidal dispersion can be done while using chemical reactions. Colloidal dispersion can be done. So which type of chemical reactions we are using by the preparation of this colloids? Okay, I will tell clearly. One is the oxidation, second one is the reduction, okay, and double decomposition. Okay, different type of reactions we are using. Hydrolysis reaction. If suppose I am preparing the arsenic sole. In this case, I am using the double decomposition reaction. Arsenic sole. See, first example I am taking double decomposition. Okay, double decomposition. See here, in this case, what I am doing? Generally, I am taking arsenic oxide. What I am doing, sir? Arsenic oxide I am taking, As2O3. This arsenic oxide is treated with, I am going to treating with H2S. Okay, I am treating with H2S. How I am treating, simply I am sending, okay, H2S gas. Stream of H2S gas I am sending through the As2O3, means arsenic oxide. Then what happening here? Okay, double decomposition. Okay, double decomposition takes place, and what happening, sir? Arsenic sole is forming. What is the formula of arsenic sole? Do you know? As2S3. See, this sole is forming. Plus, okay, H2O is forming. In this case, what is forming, sir? H2O also forming. Along with arsenic sole, okay, what is forming? What is forming? Water is forming. What is the color of this As2SO3? Yellow color. Yellow color. Colloidal solution is forming. And next example I will take. Let us discuss about that one. That is nothing but reduction. Okay. So for example, I want to prepare, okay, reduction. I want to prepare aluminum sole. In this case, I am taking aluminum chloride. Okay, 2 moles of AuCl3. I am treating this aluminum chloride. Means here reduction we are doing. Okay, reducing agents. Okay, I am taking the formaldehyde as a reducing agent. Okay, 3 moles of formaldehyde. Then what happening, sir? Here it is forming aluminum sole simply. Okay, what is the formula of aluminum sole? 2 moles of Au. That's it. What is removed from this one? AuCl3, Cl, chlorine can remove from the whatever it may be formaldehyde. Then what is the forming, sir, here? Okay, this is the sole, aluminum sole, and as well as it will be gives, okay, it will be gives formic acid as well as hydrochloric acid. Formic acid as well as hydrochloric acid is formed. See, this is the one of the preparation of, okay, aluminum sole. Okay, so this is reduction method. What we used here? Reduction. Here decomposition, double decomposition takes place. Next, third example I am going. Okay, now oxidation method. By using the oxidation method, I am going to prepare the colloidal solution. If suppose I am taking SO2, okay, I am going to taking SO2. This is the oxidation method, beta. Oxidation. See, in this case, what happened? This SO2 is I am going to treating with, okay, so generally H2S gas. Okay, generally I am sending both are gases, SO2 and H2S. So this SO2 gas is treated with H2S. What happening? The oxidation takes place. Here what is forming? Sulfur sole is forming. What is forming? Sulfur sole is forming. Preparation of sulfur sole. What is the formula of sulfur sole? Do you know? 3 moles of S. Okay, this is formed. Sulfur sole. Plus, what is forming, sir? Okay, H2O is forming. Again, in this case also, what is forming? H2O. Here I am writing the 2 moles of H2O. See. Are you getting? So, here I will take 2 because 3S. The formula should be 3S. This is the sulfur sole. So, these are the methods to prepare the chemical methods. These are the chemical methods or aggregation method or aggregated methods. So these are the some examples. Now we'll go to the next point. Hydrolysis. You told sir, hydrolysis also one of the chemical reaction. In this case also we may prepare sol or colloidal solution. Okay. See, now this is also nothing. Simple thing. I am going to taking the FeCl3. This is the hydrolysis method. Okay. So in this case what happening, in this method, simply we are taking any salt. Okay. When we are going to taking the salt, okay, this salt is treated with water or solvent. Okay. In this case what happening? Hydrolysis. In hydrolysis case, what is the solvent, sir? Water only. Yes, am I right or not? So, if suppose I am preparing the ferric hydroxide sol, ferric hydroxide. Okay. So, in this case, I am going to taking FeCl3. I am treating with water. I am treating with water. Then what is forming, sir? FeOH taken twice. Are you getting my point? This is called as a ferric hydroxide sol. Okay, this is in the red color. Red sol is forming. So, we can now balance the reaction. So, what is the FeCl3? So, here I am going to taking the 3 moles of H2O. So, what is the again product, sir? HCl is forming here. Okay, am I right or not? 3 moles of HCl is forming. Okay, this is the hydrolysis method. In this method also we are getting what, sir? Colloidal solutions. Okay, next method we will discuss. Okay, so in the next method, what is that method, sir? How we will prepare the colloidal solution? The next method is nothing but Briggs-Arcs method. Okay, what is this, sir? This is also called as electrical disintegration method. Or, okay, one of the scientists is there. Okay, this is called as a Briggs-Arcs method. Simple I will explain this one. So how can, if suppose, generally, in this case we are preparing the metal sols. What I am telling here, listen carefully, metal sols. So simple I am going to taking one container. Okay. In this container, okay, so first of all I am keeping this container in ice bath. Where I am going to keeping better? I am going to keeping in the ice bath. See, these are totally ice. This bath is okay filled with ice. See. So, in this I am taking some particular solution. Solvent. This solvent is nothing but water. This is a deionized water. Okay, deionized water. What I am taking here? Deionized water. And I am keeping 2 electrodes. Okay, I am going to keeping 2 electrodes close to each other. While passing electricity, what happening? Here one arc is producing. Between these electrodes, arc is formed. So in this, when its arc is forming, so particular metal can vaporize and it is mixed with water and is forming the colloidal solution. Okay, am I right or not? So this is the very easy method. Okay, to prepare the sol. Okay, so these 2 metal electrodes. These are the 2 also metal electrodes. Okay. While passing the electricity, what happening? Arc is producing. Okay. So in this arc, what happening? Due to this arc formation, one of the metal will be vaporized. When it is vaporized and it is mixed with deionized water, what is forming? Colloidal particles are forming. In this way also we are preparing the colloidal solution. So next method is there, peptidization. So what is the peptidization, sir? See, we will discuss about the peptidization. So in the peptidization, in this method, what we are doing, simply we are taking freshly prepared precipitate. Okay, freshly prepared precipitate. I am writing PPT. So now this PPT is treated with solvent. Okay, or dispersion medium, DM. So when I am going to treating with the DM, okay, this freshly prepared PPT, now I am going to preparing the colloidal solution. When I am treating with solvent or dispersion medium, I am using little bit electrolyte also. Little bit electrolyte. See, so Why? Because this electrolyte and this PPT has common ions. If suppose I want to prepare the FeOH3, okay, or iron salt, okay, FeSO3, FeOH3 salt. So for example, here I am going to taking one solution. In this solution, FeOH3 is formed already. What I am telling, sir? FeOH3 is formed. Okay, FeOH3 PPT is there. Now what I am doing? I am taking the FeCl3 electrolyte. So now I am adding this into the another solvent. Okay. So now what happening? Colloidal particles can forms. Okay, like this. Okay, means what is going on here? We are using the electrolyte. Okay, using this electrolyte, what happening? Common ion will be there. Here also iron, here iron also common ion will be there. So this common ion is utilized from the electrolyte and peptidization takes place. Okay, generally we may know that one. Actually peptidization is nothing but it is the process of converting. Okay, it is a process of converting freshly prepared precipitate into colloid solution by shaking with dispersed medium. Okay, shaking with dispersion medium in the presence of a small amount of electrolyte. Okay, that electrolyte is nothing but this FeCl3 we are used while preparation of FeOH, and means ferric hydroxide, solar ferric hydroxide, okay, colloidal solution. Okay. Now let us discuss purification of colloidal solutions. Purification of colloidal solutions. Okay, in this generally we are using two methods. The first method is dialysis. What is the first method, beta? The first method is dialysis. So what is the dialysis actually? Dialysis, it is a process. Okay, it is a process to remove okay, dissolved ions in dissolved ions. Okay, these dissolved ions are where, sir? Actually, okay, dissolved ions by Sol. Okay, dissolved ions by Sol or colloidal solution. Okay, so how they can remove? Okay, so dissolved ions, okay, we are removing by Sol. Actually we are removing, okay, generally these whatever it may be ions which are impurities, generally we may call impurities. What we are discussing? Purification of colloidal solution. Okay, so now it is a process to remove dissolved ions. These ions are the impurities in a colloidal solution. These are removing by the dialysis process. Okay, so here diffusion takes place. What it is takes place, sir? Diffusion takes place. If suppose, see how we are going to dialyze it. Okay, dialyze. See, for example, I am taking one container. Okay, I am taking one container. This container is filled with full of water. So what I am doing here? Okay, I am taking, so the bag of parchment paper, otherwise semi-permeable membrane containing bag. Okay, semi-permeable bag. In this bag, it is filled with colloidal solution. It is filled with what, sir? Colloidal solutions. See. So now what happening? When we are going to keeping like this, okay, we are dipping this bag in the water. So the whatever it may be ions present in this or impurities present in this bag can diffuses in the water. Okay, it can comes here. Okay, so here what happening? The concentration of ions will be increases. Are you getting my point? This is a SPM bag with colloidal solution with Sol. Okay, this is the water. This is the water. Are you getting my point? So now what happening in this case? The water, it may be ions diffused, okay, and it is comes to the water. When I am continuously flowing the water, okay, continuously, okay, so I am keeping, otherwise what we will do, we can openings, we will keep the openings here, okay, like this, okay, we will send the water through this from here. If suppose water will comes out, okay, from the outlets, from inlet, what we are doing, water is sending continuously, okay, continuous flow of water, flow of water. Then what happening here, the whatever it may be concentration, the concentration of ions becomes 0 up to concentration of ions or impurities becomes 0, okay, till that we are sending continuously water. Are you getting my point? Are you getting my point? Till that we are going to sending, okay, continuously water, okay. So what happening, these ions are coming, okay, outside of the bag, and the concentration is increased here while flowing the water continuously. What happening, concentration becomes 0. This is the one method. And next method is nothing what, okay, electrodialysis. See, for example, in this case I am going to talk about the example, ferric hydroxide soil, okay. Are you getting my point? Ferric hydroxide soil can be purified in this method only, okay. If suppose example FeOH3 soil can okay, purified through this method, purified by this method, okay. General thing is there, okay. Next method, so same, this is also dialysis method, but here we are taking electrodialysis, okay. Next method I am going to talk about the next method. Next one, electrodialysis or dialysis. In this case what happening, simply we are influencing the electric potential or electric field potential, okay. So while influencing the electric field or electric potential, okay, what we are doing, dialysis we are doing, means impurities are removing. In this case also we are removing the impurities. In this case what we are doing, simply we are taking one container, okay, we are taking one container. In this container first we are going to keeping, okay, semi-permeable membrane, okay, bag with colloidal solution. This is totally what, sir? This is totally colloidal solution, okay. This colloidal solution is with impurities, okay, like ions, positive ions or negative ions are there. Are you getting my point? Now here we are going to keeping, okay, metallic screen. What we are going to keeping here better? We are keeping the metallic screen or metallic gauze. See, okay, metallic screen or metallic gauze we are going to keeping. So now here, see here, both sides I am going to, okay, keeping the outlet and inlet, okay. See, this is a metallic gauze or metallic screen, metallic gauze or metallic screen. Now when I am going to connecting this one with the, okay, small battery, what happening, the charges can move, okay. It is a, if suppose negative and positive, okay, one is working like a negative, one is working like a positive. This is a positive, this is a negative. Now it is a inlet water, okay. This is the water, it is the outlet of water. In this case, inlet of water this side, the outlet of water this one, Water is outlet from this side. Okay, outlet. So now the here also totally water is there. It is filled with the water. When we are passing the electricity through this metallic gauze or metallic screen, okay, what is this, sir? SPM, semi-permeable membrane. Okay, so what happening? The negative particles or negative ions can move towards the positive metallic gauze or metallic wire, and okay, this positive particles can move towards the minus, okay, charged, whatever it may be, metallic gauze or metallic wire. So means here what happening, the acceleration of ions can take place, okay, very speedily, okay, more compared to normal dialysis. In this case, okay, the acceleration of ions is more, okay, or greatly accelerated in this case. So that's why the dialysis takes very easily. But in this case, one of the, okay, very important thing, in this case, we may not, what I am writing, in this dialysis, we may not, okay, remove, okay, impurities like non-electrolytes, okay, or we may not remove non-electrolyte impurities, electrolyte impurities like urea, okay. Why? Because the urea is not having any charged particles. Ephemerate or not, no any charges there. That is not a ion, okay. So that's why what happening, there is a molecule, but here not moving. In the dialysis case, not only ions, molecules and atoms also will remove, no problem. Any type of impurities will be there, okay, we can remove from that method. Are you getting my point? This is the very important thing, okay. Electrodialysis as well as dialysis, two methods we are using, okay, to remove the impurities from sol or colloidal solution, okay. Let's talk about the properties of colloidal solution. Properties of colloidal solutions. See here. So generally these are the properties are different. Generally, see here, general properties are there, okay, as well as electric properties are there, optical properties are there, okay, as well as, okay, kinetic properties are there, and charge on the particles also there. These are all the properties different. Today we'll discuss general properties, okay, and optical properties. We'll see, and as well as, okay, kinetic properties also. See, first I am going to talk about the general properties, okay, general properties of colloids. Properties of colloids. What are the general properties, sir? One by one we'll discuss. First property I am going to talk about that one, heterogeneity. Okay, we know that one. First property, heterogeneity. We know that one. Actually, all colloidal solutions are made by two components. One is the dispersed phase, okay. Second one is the dispersion medium. Ephemerate or not? Okay, two components were there, dispersed phase and dispersion medium. Yes. So already when we are discussed about the colloidal solution, I told you very clearly, colloidal solutions are heterogeneous in nature, because due to these two components, Okay, dispersed phase particles are larger size. Okay, am I right or not? Then dispersion medium. Are you getting my point? So due to the bigger size particles, what is forming? Heterogeneous mixture is forming. Are you getting my point? Okay, due to these two components, okay, dispersed phase particle size is more than dispersion medium particles. So that's why what is forming? All colloidal. Okay, when we are going to talk about the colloidal solutions, all colloidal solutions are heterogeneous in nature. So that's why heterogeneity. There is general property. When I am going to talk about the general property, first heterogeneity. So all colloidal solutions are heterogeneous. Okay. Now we'll go to the next point. That is nothing but, see, filtrability. This is the second one, filtrability. Generally, these colloidal particles may not be filtered by ordinary filter paper. Okay, see, colloidal particles may not filtered by ordinary filter paper. Okay, filter paper. Why, sir? Because generally the size of the particles are 1 nanometer to 1000 nanometers in the case of colloidal solution. Okay, like this. Okay, particles may not trapped by the ordinary. It cannot trapped by the ordinary filter paper. Are you getting my point? But when we are using, okay, ultrafilters, okay, so that time we may, okay, filter or trap the colloidal particles. Okay, ultrafilters. Okay, while using the ultrafilter, in the case ultrafilter, what we are doing in this case only, we may filter we may trap the colloidal solutions. Okay. Next, third one, where I am going to talk about the next property. So that is nothing but the diffusibility. Diffusion. Yes. We know that one. What is the diffusibility, sir? Okay. So generally, they can diffuse. Simply, they can, okay, diffuses in a particular solution. Am I right or not? Particles. But when I am going to comparing with the true solution particles. Okay. So diffusibility of the colloidal particles is less than okay, true solution particles. Okay, they may not diffuse more. Means compared to true solutions, they may diffuse less. Next property I am going to discussing, that is the surface area. Okay, what is that? Next one is the surface area. Okay, generally what happening? See, in the case of surface area, when I am going to talk about that one, okay, generally the colloidal particles containing especially colloidal particles contains large surface area. Okay, colloidal particles contain large surface area compared to other solutions. Okay, so that's why what happening, due to the large surface area, okay, the adsorption takes place more in the colloidal solution. Okay, on the surface of colloidal particles. Why? Because the colloidal particles has, okay, large surface area, or they contains the large surface area. So means simply what happening, foreign materials will come okay, and occupies the surface area of, okay, colloidal particles. Now let us discuss about the next point, concentration. When I am going to talk about the concentration, see, concentration of, okay, when I am going to talk about the concentration of colloidal particles is very small. Okay, these are very small. Colligative properties. So generally in these properties what happening, so these depend upon the particles, the whatever it may be, okay, properties depend upon the particles are called as colligative properties. Okay, generally colloidal solutions also showing the colligative properties, but these are negligible. Okay, why? Means partially negligible. Okay, the whatever it may be, colligative properties of colloidal solutions are partially negligible. Why these are partially negligible, sir? Because when we are going to comparing with true solutions, okay, these solutions show more, okay, colligative properties. Am I right or not? But in this case also, except osmosis, okay, except osmosis, okay, all properties are negligible, partially negligible. Are you getting my point? Okay, or osmotic pressure, I will take here except osmotic pressure. Okay, all colligative properties of the colloidal solutions are negligible. Why these are negligible? Due to the bigger size of the dispersed phase particle. Okay, large size of the particles. Due to large size of particles. Why? Because colloidal solutions have the large size of particles. Okay, when the particle size is more, okay, some particular properties are not dependent on the whatever it may be, okay, colloidal solution. Okay, it is not dependent. Okay, colligative property is nothing but the properties which are dependent on the particle's nature, particle size, whatever it may be. Okay, these are depend upon the particles. But here larger size is there, so that's why it is not depend. Okay, it can depend, but compared to true solutions, these are less. So that's why partially negligible. Only osmotic pressure is the except case or exceptional case. Okay, now we'll go to the next point. Now we'll talk about the color. Generally, okay, colloidal solutions shows different colors. Why these are showing the different colors, and different colloidal solutions are showing the different colors? This is due to actually what happening, the particles have the particular wavelength. When we are sending, for example, light, okay, through these particles, they may scattered. Okay, what happening here, the particles can absorb first the whatever it may be light energy, then after that it can scattered or emit, okay, with different colors. So in this case, okay, what happening, they are showing the colors. Simply I will tell, okay, depends on their wavelength. Okay, depends on particles wavelength. Okay, or depends on wavelength, they are showing different colors, as well as particle size. Yes, depend upon the particle size. Okay, depends on particle size. These are showing colors. These are showing the different colors. If suppose, for example, when I am taking gold soul, for example, gold soul, when I am going to talk about the gold soul, generally gold soul is in red color. Yes, am I right or not? It is in the red color, but sometimes it is showing the mixture of blue and red color. Mixture of blue and red color. Why? Because, okay, that is depend upon the particle size. Okay, so generally it is in the red color. Okay, some cases, in some times or in some cases, it shows mixture of blue and red color. Blue and red color. Blue and red color. This is the very, very important thing. These are the general properties. Now we'll talk about the, okay, optical properties. Optical properties. See, what are the optical properties are, sir? Okay, we'll discuss. Optical properties. See, here in the optical properties, we'll talk about only one and only optical property, that is nothing but Tyndall effect. Tyndall effect. So what is the Tyndall effect, sir? Okay, what is the Tyndall effect, sir? See, suppose I am taking two solutions in a container. Okay, in a different container, I am taking two solutions. See, this is a true solution. If suppose in this container I am taking two true solution. Okay, this is a true solution. And in another, so in a true solution, particles may not observed by the normal microscope also. We know that one. And it is not visible. Particles also not visible. Okay, this is a true solution. I am taking like this. Okay. Okay. This is a true solution. And in another container, I am taking another container, I am taking, okay, colloidal solution. Okay, these are the colloidal particles. Okay, these are all colloidal particles. Okay, are you getting my point? This is a colloidal solution. Suppose solution. Now I am sending, okay, beam of light. Okay, I am sending beam of light. Which beams are strong beam of light I am sending? Okay, strong beam of light. Okay, this is the strong beam of light, beta. So now in the true solution, it is invisible. It is invisible in true solution. Okay, again we are continuously, it is, okay, enter into the true solution and it is going through this solution also. Okay, if suppose it is like this. Now what happening, sir? Here the particles are there. Okay, it is moving like this. Okay, so it is also moving like this, if suppose. What happened here? These particles, see. Now I am going to talk about in this area, whatever it may be, particles are present. Okay, so like this. Now they emit the light. Okay, so they emit the light in all directions. Okay, in all directions, what happening? They are emitting the light. This effect is called as Tyndall effect. Okay, this effect only called as a Tyndall effect generally. See, here also. Okay, so See here. Now, when we are sending a strong beam of light through the true solutions, no any scattering takes place or no any emission of the light takes place or light energy takes place. But when we are sending through the colloidal solution, okay, the emitting of light or whatever will be scattering of light takes place in all direction. Okay, this phenomena is called as this phenomena is called as Tyndall effect. Okay, Tyndall effect. See what happening here while sending. Here I am writing while passing strong beam of light through colloidal solution. Okay, the light can emitted all directions. Okay, colloidal solution. Okay, light can emitted all directions. Okay, so means what happening here? While passing the strong beam of light through the colloidal solution, okay, light can emit, okay, or light can emitting in all directions or emitted in all directions, okay, is called Tyndall effect. Okay, are you getting my point? But in the case of true solution, it may not happen. Why? Because in the true solution it's not happening, okay, due to small size of the particles. Okay, true solution contains small size of particles. Okay, small size of particles. These particles are less than wavelength of light. Are you getting my point? But in the case colloidal solution, what happening? Particle size are large. Are you getting my point? Particles size is large. Okay, and these are bigger than wavelength of light. Okay, these are bigger than wavelength of light. Are you getting my point? So actually here two cases I want to discuss. So when the Tyndall effect is possible, okay, for example, any solution is showing the Tyndall effect, okay, the solution must and should obey the two conditions. So first condition is nothing but, okay, the refractive index of RF, refractive index, okay, RI, okay, refractive index of dispersion medium and dispersed phase both are is there similar or not? In this case what happening, you know, the refractive index of dispersed phase and dispersion medium must differ. Okay, what happening? Refractive index of dP and dm, okay, must differ. Dispersed phase and dispersion medium must differ. Okay, means in this case the refractive index is not same of dispersion medium and dispersion phase. This is the first one. Second condition, what I am telling you. So this is a very important. Okay, diameter of particles. Okay, diameter of particles. Okay, more than okay, light particles. Okay, or not smaller than, much smaller than wavelength of light. Or what I am telling here? Diameter of colloidal particles or particles not smaller than wavelength of light. In this both cases only, what happening, you know, when the solution can obey these two cases, okay, that particular solutions may show Tyndall effect. Okay, now we'll go to the next point. Next property is nothing but now kinetic property. We'll talk about the kinetic property. In this kinetic property, we'll discuss Brownian movement. So what is the Brownian movement, sir? Next one is the kinetic property. properties of kinetic properties. Okay, in this case only one property is there. We'll see kinetic properties of soles or colloidal solution. See, one and only property, that is a Brownian movement. Why it is called as Brownian movement means, first it is observed by the British scientist Brown. Okay, so that's why honor of him we given the Brownian movement. Okay, see, Brownian movement. See, if suppose when we are going to observing colloidal solution through the microscope, okay, so what happening, the colloidal particles, okay, can move in the continuously, they are moving in the rapidly they are moving. Okay, see, here one particle is there, it is moving. Okay, here it is moving. Okay, so the particles are moving continuously in the zigzag manner. Okay, so the motion or that movement of the rapid movement of or continuously rapid movement of zigzag is called as, okay, Brownian movement. Are you getting my point? Continuous zigzag movement of particles, movement of colloidal particles, okay, is called, okay, Brownian movement, called Brownian movement. Okay, Brownian movement. Yes, so means these are not in the stable. Okay, they are not located in one place, the particles continuously they are moving in the zigzag manner. Okay, it can observed by the Brown, so the scientists, so that's why this movement is called as a Brownian movement. Okay, generally it depends upon the particle size. The Brownian movement depends on the particle size. Okay, it depends on the particle size, not nature. Okay, particle size. Okay, not nature of the particles. Okay, so another thing I am telling, generally the Brownian movement, okay, it is due to unbalanced bombardment of the particles. Okay, due to unbalanced bombardment of the particles, it takes place in the colloidal solution. It is a very, very important. So let us stop here. Okay, in the next class we will discuss, okay, remaining properties of colloidal solutions. I think you may enjoy this class.